Canvas will automatically assign a grade to the rest of the students in the list. So yeah, your hypothesis might be correct, but it kind of got picked up.
Well, we know for the next one.
Let's do a practice submission.
Yeah. We should. How do we get the first test? We get like a pair of test students?
Yeah, let's do another test. Oh no, I thought you did.
Maybe
has like all the different
The way to put this thing down, right? It was just
there's a way to put it down. What is trying to do on the board?
Wait, assigning individual grades.
I mean, we can definitely decide. There's only 24. We can 21 times. It won't be that much more time, but we just want to protect who doesn't need these people sign up.
Are we individually creating PDFs? I forget if we specify. They have the same set of
you can never know which one.
Or they should have 2 seconds. Like he said that he said that people probably submitting either one PDF file or 2 PDF files in the submission. There should be something.
whatever it'll say on the PDF.
I know that in class you said that you could do it in the same document. So people
Group submission. Sign up for the project group. All names mentioned. In the PDF, each group member is expected to provide their own response. So I mean, theoretically, we'll have to assign everyone.
Okay, let's get started. How's everybody today?
That's 30.
Good. You guys hear me back there? Good. Okay, let's start with some announcements. Homework 1 grades are up. You should be able to see them. Nods. Okay, good. Let's see. There's also an answer key now in the files folder under homework solutions, I believe, subfolder. Take a look at that. Policy on regrading. So there is an option available to you as of what I've just decided for you to petition for a regrading on a specific subproblem or a set of specific subproblems, in which case I will grade them. However, we will completely throw out the old grade and I will assign a new grade based on my judgment in that case. And having kind of gone over the way a lot of things are right now, I can say that the TAs were pretty generous regarding partial credit. So I'm happy to regrade whatever subset of your homework you would like, if you feel like there was something that wasn't fair or whatever. But keep in mind that there's a significant chance that your grades will change for the worse rather than for the better. Does that make sense? Okay, cool. So there were some things that I think kind of surprised me on the results of the homework. So let's look. All right, in graph search. So I did a bunch of examples that were just like this in class, right? We spent almost an entire day on this kind of thing. One of the things that I think a lot of people messed up potentially is this notion of tie breaking when we're adding things to the data structure that we're keeping track of our frontier on. That's the Q. or stack or priority queue, depending on the algorithm, right? And so we had to break that tie in some way. We specified that when extending states, add them to the data structure in alphabetical order if you need to resolve a tie, right? So that's add them to the data structure in alphabetical order. So if you're looking at DFS, which is a stack, that means you're going to pop them off in reverse alphabetical order if they were added at the same time, right? Does that make sense? That is different from last year's homework, which specified something similar to this with the opposite convention, which is that you remove things from your data structure in alphabetical order. So that brings me to my next point, which is that a lot of wrong answers were suspiciously like the right answers from last year. So maybe coincidence, just keep that in mind, that we've changed these. So sometimes they look the same at first glance, but they are not. Okay, so you should actually do them. All right. So we can go through any of these. Right now, if you'd like. I also want to look at this. So the wrong answers on this question really surprised me as well, because I basically gave the right answers for every single one of these in class. And I didn't hide it. I said these are the answers to the homework while I was doing it. So we can go over these as well. Specifically, one of the things that I wanted to touch on is this here. If we restrict Alice's set of actions such that she can only accelerate, or she can only decelerate after she's finished accelerating, so you can't alternate between the two anymore, you do all of your accelerating and all of your decelerating, does that change the set of reachable states or the set of unreachable states by symmetry? So let's look at the very well drawn out solution key example. Thank you, Zach. Here's the idea. So basically what we did here is we showed the whole set of reachable states and kind of a strategy for reaching them. And the question is, does this set change if you're not allowed to accelerate after you've decelerated? And the answer is no, it does not. So the set of reachable states remains the same. And it should be noted that reachable does not mean reachable by some specific path. It just, is it reachable by a path obeying the constraints of the problem, or is it not? Reachable also does not mean can then go on to finish the problem by reaching another state, like the goal state or something. That doesn't matter. It's just, can you land in a specific state given the rules, right? Does that make sense? Okay, so you should read this. It's very good, but basically the idea is that we've described here the fastest way to get to a given velocity with respect to position, or vice versa. So if you always accelerate, then you're going to end up with as high of a velocity as is possible, as early as is possible. Does that make sense? So what that means is that anything, if we look at this state here, anything in this region of the state space cannot be reached, right? Under either set of rules. You can't get there faster than this, so that completely precludes this entire quadrant here, right? Similarly, if you look at this state, there's this quadrant, right? Unreachable. Make sense? Right? Similarly, this one, right? So the question becomes then, those aren't reachable in either case. Do we have a strategy for reaching every other state given our restricted set of rules? And what Zach has done here is described that strategy exactly. So basically, you can accelerate to 1 and then decelerate at any point. You can coast from there and then decelerate at any point, or you can keep on coasting, right? To reach any of these above states, you can then, at the prescribed time, accelerate. Make sense? So they're all reachable under this new strategy. There are no states that are unreachable under the restricted set of actions that are reachable under the unrestricted set of actions. If you find one, it would surprise me, but bring it to me. But I'm confident they don't exist. So, all right, does that make sense? Okay, so did we want to do this in class now? Okay, so feel free to come to my office hours. I'm happy to work through these. The TAs are happy to work through these in their office hours. Take a look at the solution sheet with respect to your answers. If you believe that there's something that doesn't match up, come to me, come to my office hours, send me an email, whatever. I will happily regrade that sub-problem. But I will do it without any knowledge of what the TAs have done in the past. Yes?
Is there a time limit you want to enforce?
Sure. Yes, that's a good point because I don't want to be grading everything the day before grades are due. So let's say you have one week from today. Does that sound good? Okay. To ask you, and then I will grade them, not necessarily within 1 week of today, depending on the demand. But okay. Cool. Yeah, so that state space reachability question is basically the only part of problem 2 that I didn't explicitly answer, although I kind of implicitly answered it in class. The other ones I did, and then we did examples based on problem 1. So the tricky part of problem 1, and it's not really tricky, is how ties are broken when you can't rank them with respect to one another when you're adding into the data structure, right? We described a strategy for doing that. Everything else fell out from there. Make sense? Okay, cool. All right. So, any questions on homework stuff? Great. Homework 2 should be coming very shortly, along with project 2. So, all right, moving on then. Questions about material? Okay, great. All right, so just like I was excited last week, I'm super excited this week because this week we're definitely getting reinforcement learning, unless we are the slowest at looking through like 4 slides that it is possible to be. So I was excited last week to touch on reinforcement learning. That's actually happening today. Still excited. MDPs are still fun though, so all of it's great. All right, so let's move on. And by move on, I mean recap. Okay, so we've been talking about MDPs, Markov decision processes, right? And basically an MDP is described by this set of things. We have a set of states, we have a set of actions, we have a set of transitions. These describe, given a state and a chosen action, the probability that you will land in a subsequent state, right? This, in the worst case, could be defined over a pairwise cross product of all 3 of these, your state space twice and your action space once, right? For every state, you choose among every action has the possibility of potentially landing in every other state. Right, that's kind of gross. Okay, but these are conditional probabilities. Basically, we define this transition function, but what it really is the probability that you land in state S prime given you started in S and chose A. Right? Okay. With every one of these transitions, we have some notion of reward. Right? And then in order to actually do some simulation, we also have some start state. So the idea is that we want to maximize, we want to create an agent that maximizes its expected reward as it kind of moves through the world, right? And the world has been approximated by this model. Okay, great. So we also define this set of quantities, right? So we have some policy, right? We call this pi. Policy is a function that takes states, right, and returns an action. Right? This is defined over all states, some recommended action. It can be an optimal policy, in which case it's recommending to you the optimal action under the expected value of the possible outcomes of that action, right? It could be some random policy, it could be a bad policy, it could be a good policy, it could say always take action A, it could say always take action B, it doesn't matter as long as there is an action defined over all the states. Or you have a way to compute an action defined over all the states. So if this is written down as some form of lookup table, it's explicit, you have to do some kind of computation to determine the action, right? That policy then is implicit. Right? Your policy may be the application of some code, some algorithm or something, right, that determines an action. But either way, conceptually, the policy is a function over states and maps a state to an action. Yes?
Is there something like a trivial policy? Have you had a trivial heuristic?
Well, I mean, we had this like null heuristic concept, right, which is the heuristic is always 0. This is different because it's mapping states to actions, and in the abstract, we don't know what states look like or what actions look like. So there are trivial policies where you just say go right always, go left always, do nothing always, whatever. But there's no like a capital T trivial policy. The canonical trivial policy doesn't really exist. Okay. All right. So there's no like Platonic idea of the trivial policy. Okay. Very good philosophy. Well, I may have messed up. I'm not a philosophy guy, but that's about as deep as my philosophy goes. Okay. All right. So we also have this notion of utility, right? This is the sum of discounted rewards. We have values, right? These are the expected future utility from some state, right? And then we have this notion of Q values, which are coming from Q states here, right? Which is the expected future utility from a Q state. And if we look at this abstraction here, here, right? We can relate it to our expect-max tree, search tree that we'd spent so much time on. And the idea is that we have some state here. We're going to choose an action, the best action that we can, right? And that will place us in this Q state, which is a state in which we started in S, we chose action A, but S prime hasn't hit yet, right? The consequences of our action haven't resolved, but we have chosen the action, right? And these can have their own values, right? Which is basically just the expected value over that possible. Everybody remember this? Great. Okay, so we have those quantities. We can also define them as optimal quantities, right? So the optimal value of a state then we define as V star. It's the expected utility starting in S and acting optimally from there on, right? We can have an optimal value of a Q state, Q star. Star is generally used to represent some optimal quantity. This is the expected utility starting out from the Q state, which in other words is having taken action A from state S and acting optimally thereafter. So what happens right now, we don't know. That's stochastic, right? But whatever happens, we're going to act optimally from there. This is the value, expected value of that, right? Okay, and then as I mentioned, we have this notion of optimal policy, which is the optimal action from state S. Well, the optimal policy is a function over states. The optimal action from a state is what's described by the policy given state S, right? Does that make sense? Cool. Okay, we also talked about this notion of Bellman equations, right? Which defines the optimal utility via this expecting max recurrence. It's basically described by this figure over here, given one step look aheads, right? So if we try to derive this again, we have E star of S, right? This is, so we get to choose A. We want to do the optimal one, right? So we're going to take the max over A, and then we need the value of this node here, right? Whatever that optimal choice of Q nodes is, right? But since there's stochasticity here, and we can end up via some probability landing in a whole set of S primes, we have to take the expected value, right? The expected value looks like the weighted sum over the possible outcomes of the transition probability, starting in S, taking action A, landing in S prime, right, times the reward we're going to get for that transition, plus what happens if we act optimally in the future from there, plus some discounted value. Right? Does everybody remember this? Okay. And so, again, to reiterate, this is very important. The idea here is that the value of here assumes we're acting optimally. So that is kind of encoded here, right? we're going to take the action that maximizes the expected outcome given that choice of action, right? That expected outcome, the value of the expected outcome, right, is the expected value. That's kind of encoded here, right, where you take sum, the weighted sum, where you're weighting by the probability of the thing occurring, of the value of the thing, right, where that's the value. Okay. And I guess here we express it with respect to the intermediate Q states, which we could also do. I wrote it in line, but you can break out the value of the Q states here, right? And so we're relating B stars to our Q stars, and our Q stars to the next steps B star, right? Written in line is what we just did. And that's this here. This is the Bellman equations. Right? Okay. So they characterize optimal values with respect to other optimal values, but it's not really describing how to solve them, right? It's just a characterization. So we came up with this algorithm called value iteration, which is this idea that we know the value, we have 0 time steps remaining to us, and then we can relate the value 1 time steps remaining to us by that value, and then we can take those values, write them down, relate the value associated with 2 time steps left to those ones, right? And on and on. This describes a dynamic programming problem, right? Because we're repeating all of these. We're leveraging repeated computation by having written down the things that we know, and then we reference them later, right? Dynamic programming. You guys have seen dynamic programming before, right? Okay, good. All right, so conceptually speaking, this is doing 2 things. One, it is telling us the true value associated with having k time steps left, or k plus 1, depending on which side you're looking at, right? That is the true value if you have k time steps left. But as we increase k, this is approaching the optimal value that doesn't have that depth limited concept at all, right? So we can run this over and over and over and over again, and what we're doing is we're kind of converging on the true V star values of our states and computing the optimal values given k, right? Does that make sense? It's kind of a 2 sides to the same coin kind of thing. But via the same process, the same algorithm, you're getting 2 pieces of information. But they're approaching the same thing, right? Okay. So we repeat this process until we converge. A quick refresher on the complexity. What's the complexity of 1 step of this? Let's look at the equation. We have to consider all the A's, right? So if the set of A's is capital A, then we have the cardinality of A as 1 factor, right? We have to consider all the possible landing points for every one of those, right? In the worst case, every possible A will transition to every other possible state, right? And so if we have a set of states as capital S, then the cardinality of that set is another factor here, right? And we have to do this whole thing for every S, right? So then, right? Make sense? Okay. This looks either slow or fast, depending on what your S's and your A's are, right? It's certainly better than some of the exponential things we were seeing in the past, depending on what your actual values are, but it's still really slow if you have a non-trivial size S or A set, right? Okay. And with slightly different notation, there's that type set. Okay, and we also talked about this theorem, that this will converge to the unique optimal values. I described this last time in kind of a almost proof, more of a sketch of a proof kind of way. But the idea is that our approximations are getting refined toward the optimal values. You can, in practice, bound these. That bounding shrinks as a function of the number of iterations you're performing. You contract on the optimal value. Okay? The key takeaway there, though, however, is that what we're doing is we're determining these stars, right? But what we really care about is pi star, right? Because, well, usually that's what we really care about, because we want an agent that's able to act, right? And so we're using these to determine this, because this is the thing that will actually run our robot, for our game AI or whatever it is. And the issue is that our policy is going to converge long before our values do. So there might be something better that we can do. Okay, and so that is where we stopped, right? So now we have this notion of policy evaluation. So we're going to kind of take that weak point for value iteration, and we're going to maybe look at how we can improve it. All right, so we'll start with this question though. Given that we have a policy, somebody hands us a policy pi, how do we compute the values for the states in this state space given that policy? Right? The values are defined with respect to the policy, so if we're given the policy, we should be able to calculate the values. Right? So this looks the same except for we're not maxing over some set of actions, right? That action is described for us by the policy. So we touched on this a little bit last time, but the idea is that we turn these recursive Bellman equations into updates, similar to how we did in value iteration, right? But now instead of v star, we're doing v pi, right? This is the values with respect to some policy pi, right? We know the values given that we have k equals 0 time steps left. We can do this same recursive update, right? Except for now, instead of maxing over a, we have a defined for us. So the max term disappears entirely. Every time an a was a choice that occurred before, we now have it described by the policy pi, right? And so that equation got a little bit simpler. We had basically this entire thing, right, but preceding it was this max over a. That doesn't seem much different, but in practice it can be very different because with that max, this set of equations is nonlinear. But if we get rid of the max, this is now a linear set of equations, and there's all kinds of pre-built, very fast linear system solvers that can be applied to it. Couldn't be applied before. Okay. Additionally, it got computational complexity. With respect to computational complexity, a little easier as well, because you're not considering a's anymore, right? So that a term in our big O goes away. Make sense? And that's described here, right? So our a term is not like that. So depending on our s's and a's, this might be much more efficient than it was. Okay, and as I mentioned last time, and just now, without the maxes, these are just a linear system, and so you can leverage linear system solvers. Okay. All right, so now, I guess that was still review. Here comes the new stuff. We're going to define this algorithm called policy iteration, and this is going to be an alternative approach for calculating our optimal values. So we're going to get v stars out eventually, but in practice it's going to work much faster. And the idea is, as given by the name, we're going to kind of iterate on suboptimal policies, improving policies, evaluating the improved but still suboptimal policy, interleaving this notion of improving policy, evaluating the quality of the policy, improving the policy, evaluating the quality. Make sense? Policy iteration. Okay, step one, policy evaluation. So that's what we just talked about, right? You can calculate the utilities for some fixed policy. These aren't optimal utilities. They're utilities with respect to that policy, right? Until they converge. So this is value iteration, right? Except for a fixed policy evaluation, right? This is an iterative process defined by those update equations we just saw. But we can run these until they converge. And in practice, this can be much faster than value iteration because we're not considering all of the possible actions at any given step. We're described an action. It is given to us as simple, right? Okay, so we do that until it converges. And then we improve the policy. So we update our policy using a one-step look ahead, similar to the look aheads we were doing in the value iteration computation. We're using, however, this evaluation we computed in step one and updating our policy. So we improve our policy using a one-step look ahead given the values we computed in step one, right? And we do it again, and again, and again, and again, and again, and again, and again, right? Okay. This is policy iteration. It's still optimal. And in practice, it can converge much faster under a lot of conditions than value iteration. Okay, so now we have two strategies really for identifying our values, right? Value iteration and policy iteration. Okay. So a little more in detail, the idea here is that this is our policy evaluation, right? We iterate it until it converges. Then we do a one-step look ahead here, right? Where we update our policy using this argmax operator we described last time in order to improve the policy based on the calculations we did up here, right? Cool. Okay, so both value iteration and policy iteration compute the same thing, right? We're computing V stars for all the states. In value iteration, every iteration updates both the values and implicitly the policy as well. You don't really track the policy, but you can take the max over the actions at any step in order to kind of extract the policy from the V stars, right? In policy iteration, we do several passes, updating the utilities with a fixed policy. Each pass is faster than a value iteration one because we're considering only one action, not all of them. And then after the policy is evaluated, we choose a new policy based on this one-step look ahead and evaluate that. Yes?
On the last slide, the like Y-looking Greek symbol of the last term, was that one that like replaced the discount gamma?
So that is gamma.
Okay.
That's just the fonts, gamma. Yes?
So with a fixed policy, do we just start off with some random policy for this pattern?
Maybe? Yeah, maybe you start off with some lowercase t trivial policy like we were talking about earlier. Maybe you start off with something random. Maybe you start off with a good guess that was computed by something previously. Maybe you start off with a policy that worked well for something related, like a different robot that looks similar, or a different, where you have the same state and action space, or a different environment, or slightly different, these kinds of things. It really depends. But in the worst case, you can start with some random policy, or you can start with some fixed policy that's not very good. You could run this in parallel a bunch of times with different initializations, get different values, right? It's all kind of up to you. Yes?
So at each stage, how are we checking, how are we changing the policy? Are we just like varying what it should be by one step, like one action?
Yeah, so we look ahead. All right, so it's this equation here, right? So we're now updating what used to be pi sub I, right, which was dictating all of the equations up here, all the calculations up here, right? We're updating it to pi of I plus 1, right? This is defined of every state. So we look at every state, right, and we want the argument, right, because the policy is describing an action, not a value, right? So we want the argument A, the action A, that maximizes this, right, where this is a single look ahead based on the optimal policy, the optimal values associated with the previous policy.
So we're kind of ignoring all possible policies, or?
No. In that you're doing calculation for every action from every state once. You're kind of considering all possible policies, I guess. But the problem is you don't really know. Yeah, so if we look at our state action diagram here, right? We have S. Our policy pi was dictating which arrow coming out of S we're taking, right? And what we're doing is we're computing the value. Can you guys see that on the edge? Yeah. We're computing the value under policy pi of every state S. So that's what's happening up here.
Okay, so we're actually computing policy for each state, so we're doing this whole thing for each possible state?
Yes.
Okay. Yeah.
But you're only doing one step of it, right? This is kind of like value iteration, in which you were considering a max over all the possible actions from every state, and then all the possible ramifications from there being an expected value. right? But that was running until it converged to some set of values. This is just once.
Do you have examples and stuff that might help us?
I will put together some examples for you for this one. Sound good?
Yeah.
But the idea basically is that, we've been taking this action, right? But there are these other actions we could have taken coming out of S. We've defined the value here with respect to this, right? Every once in a while, we're going to reevaluate this choice here, right? We're going to say, well, let's actually look at what happens over here. Let's actually look at what happens over here. Let's look at what happens over here, right? Each one of these has its own set of possible outcomes under which there are states, right? And what we're looking at is the expected value associated with these two nodes here, right? And so our policy is really an arrow for every state. And so when we do our update, our improvement of our policy, we take every state and we look at all the arrows. And we say, it turns out this arrow was better than this arrow. That's my new policy. I take that arrow from this state every time, right? But the values we computed are different. They're not exactly right. So then we have to say, given this new policy, we have to update our VPIs for every state, right? Because the policy is different, right? So the values are different, right?
We're taking it in half, right?
I'm sorry?
We're taking it in half, so.
For instance. Okay. Yeah, so I'll put together some examples for us for next time. So, that I have for you. Okay. So that's policy iteration. We improve the policy, we evaluate the new policy for some fixed time or some number of time steps or until some convergence threshold. Then we update our policy, we evaluate the updated policy over and over and over and over again. Right. Okay. Both of these are describing dynamic programs for solving MBPs. Just a different way of solving MBPs. Right. Okay, so in summary, what we want to do for MDPs is compute optimal values. From those, we can derive optimal policies. Right? So we use value iteration or policy iteration to compute these optimal values, and then we can compute values for a particular policy. This we used in policy iteration, right? In that case, we would use policy evaluation. And if we want to turn our values into a policy, we would use policy extraction, which is just this one step look at, right? Just say, I've got a state, what are the options? Just take the best one, right? You've already defined the values, so you can make that decision in a smart way in one step. Make sense? Okay, these all kind of look the same, right? We're all using the Bellman updates or the Bellman equations in just very slightly modified ways. We're all using one step look ahead expect max fragments. That is all true. So it can be kind of hard to keep track in your head of what the equations look like that relate V stars to V stars, or VKs to VKs, or V pi's to V pi's, or V stars to Q stars, or Q stars to other Q stars, all of this, right? All of these, if you understand the Bellman equations, you can derive the relationships between them very simply, but until you really kind of get your head around how this works, it can be kind of confusing because all these relationships look very similar in the math, but they differ in some pretty key ways. Does that make sense? Okay, but that's why I derived it by hand a couple times in class, so you can kind of start to build the intuition that allows you to do that derivation yourself. Right? Okay, MDPs, we did it. Now we're going to solve MDPs where we have less information. And that's reinforcement learning. Okay, let me run through an example first, and then we'll take a break. All right, who's heard of the two-arm bandit problem? Great, we're going to kind of talk about an instance of a simplified version of that. And that's going to motivate reinforcement learning. All right, so let's say you're playing slot machines. You have 2 slots you can choose from. On the left, this blue one, every time you pull that lever, you get $1. That's nice. That's better than the slot machines you'll find in it. But I'm told. Okay, on the right, there's a different machine. You pull that lever, and with some probability you get $2, and with the complement to that probability, you get $0. So you're either going to get $0 or $2 with some probability, right? So which do you pull? That's the question. All right, so we can define an MDP from this if we know that probability. And this is what that MDP might look like. And it looks a little more complicated than you would think it would, but that's just because we have different rewards depending on if we win or lose, so we have to have different stakes depending on if we win or lose. Okay? But the idea here is that our stakes are we won or we lost. Our actions are pull the blue lever or pull the red lever. I'm sure there's some matrix analog here, but I haven't figured that out. Okay. So here are our transition probabilities, right? So if we previously lost, we could pull the blue lever, get $1, and we're a winner for sure, right? Probability 1. That's nice. If we previously won, we could similarly pull the blue lever, get $1, and stay in our we won state, right, with probability 1. However, it's a little more interesting with the red lever, but regardless of where you started, win or lose, you pull the red lever with probability 0.75, you get $2, and if you weren't already there, you transition into winning, right? But with probability 0.25, you get nothing, and you end up in the lost state, if you weren't already, or if you were already. Either way, you end up in the lost state, right? Okay, does this make sense? Very simple MDP. We know the probabilities. Okay, so let's say we want to solve this, right? And so that means what we really want is an optimal policy. What that means we need is a set of B stars for this, right? So what is the optimal expected value? Well, let's not go into it that deep, actually. Let's just say we want to solve this in a more nebulous sense, and so what should we do? Let's say we have 100 time steps remaining. Let's say our policy is always pull the blue lever. What's our expected value, our expected return under that policy? We always pull the blue lever, we get to do it 100 times, we get $100. What if we always pull the red lever? 150, right? So what should we do? Should always pull the red lever. Okay, that seems reasonable to me. All right, so you guys just came up with a policy. Our expected value if we play red always is 150. If we play blue always, it's 100. This was offline planning. This was solving an MDP. We did it kind of in our heads, but we solved the MDP. We knew the transition probabilities. We didn't have to pull any levers. We just said, always pull the red one. That's the right answer, right? But you have to know the details of the MDP, right? You need to know these transition probabilities. You need to know the rewards associated with each. But we didn't actually play the game. We didn't have to, right? We could plan offline. That's different than online. Online planning is where you're actually trying things out. Offline is where you just can reason about it in advance. Right? That's the difference. This is offline. Solving MDPs offline. Right? Okay, so we solved it. Let's see what happens. What should we do? Alright, pull the red lever, we get $2. What should we do? We get $2. We get $0. Should we keep pulling the red lever?
Yeah.
Alright, let's keep doing it. Let's say we pull it 10 times. What do we get? Let's see. Well, so maybe a little unlucky, right? Because our expected value would have been 15. Still more than if we had pulled the blue lever. Right. Yeah, so we're working out. But this just highlights that reasoning we did over the MDP was reasoning over an uncertain world, right? there's this stochasticity, but we say, given what we understand about how the world works under this uncertainty, this is the optimal way to do it. So when we actually execute it, we may get something different, right? Because that's how randomness works. But we can rest assured knowing that what we did was the right answer given the probabilities and the rewards. Right? Okay, let's talk about online planning. We realized that that was a bad slot machine and the house was losing all the money, so we replaced it with a different one. Right? Now I'm not telling you what the transition probabilities are for pulling the red slot machine flip. Right? What should we do? What's the right answer?
Reinforcement learning?
Hey, good answer. Yes, but more informally, more broadly, why don't we try it out and see what happens? Right? It's not clear what the right answer is yet. Right? So what should we do? We pull the red lever. $0. What should we do? Okay, let's say we pull the blue lever. We get $1. What should we do now?
Pull the red lever.
Pull the red lever. We get $0. What should we do now?
Pull the red lever.
Pull the red lever. We get $0.
Maybe pull the blue lever.
Should we pull the blue lever? Okay, we pull the blue lever. We get $1.
Are we feeling lucky?
Are we?
No.
It's a dry spell. Pull the red lever.
Pull the red lever. Hey, $2.
I told you guys.
Do not go to Vegas for this guy. Okay, just free advice. That's not free professional advice for the day. Okay, this statement not brought to you by the school. Okay. The opinions there don't reflect the things. All right, we pull the red lever again. We get $0. What's going on? Keep going. Oh, $2. What's happening? What should we do?
Step back and now look at the values.
That would be a very insightful thing to do. But we're not that smart yet, so let's just keep pulling levers. At some point, maybe we decide we've seen enough of the red slot machine, we prefer the blue one, and we'll just go do that. Right? And so, once you switch in your head that I'm going to start pulling the blue slot machine, you don't really have a reason anymore to pull the red one. Right? Because the reason to pull the red one is either to say, I believe it's going to give me more money than the blue one will, or to say, I don't know enough about its behavior that I'm going to spend one of my choices in order to learn more about how the red slot machine behaves. Right? So conceptually, you really want to get your learning done kind of at the beginning, right? Because once you switch to the blue, there's no reason to learn more about the red, otherwise you will learn it early. Right? This concept starts to describe reinforcement learning. Okay, so what just happened? Well, let's say we played 10 times, we got $4, that's not as good. Right? So knowing now what we could have known then, we should have been playing the blue one the whole time, but we didn't know. Right? Okay, what just happened? It wasn't planning, it was learning. This is the first time we're doing learning. We've, up until this point, done planning. Hooray! Yes, specifically it was reinforcement learning. So we had an MDP, but you couldn't just solve it. You needed to figure out the specifics of the MDP before you could solve it, right? There was an MDP. Underlying that, there was an MDP. It had transition probabilities, it had rewards, right? We just didn't know it. So you can't reason about it to the same degree in advance that you could have otherwise, right? You need to actually act to figure it out. All right, so in this very simple example, we touched on a bunch of really important concepts that come up in reinforcement learning. Exploration. You have to try unknown actions to get information, right? We had to try the red slot machine in order to start to build an understanding of how it was behaving so that we could keep making better and better choices, right? But we also had this concept of exploitation, which is basically we say, given what we understand about this, it's time to do the thing that we think is best in order to actually accumulate reward, right? We can't just spend all of our time learning how the system behaves. At the end of the day, you want to accumulate reward, right? So there's this trade-off between spending computation or iterations or money or whatever in order to explore the world, to learn more about how it behaves, and this notion of spending those same cycles of whatever in order to exploit your knowledge of the system and actually get things done or accumulate reward, right? Okay, so this concept of this trade-off between exploration and exploitation, this will come up a lot in the future of this class. Okay, we also looked at regret, right? Even if you learned intelligently, we made mistakes, right? We spent all that time pulling on the red slot machine's lever. That was the wrong answer. You just look at the expected value, right? You should have just been pulling the blue the whole time. That's the notion of regret, right? We acted suboptimally in order to learn more about the system. We had this notion of sampling, right? Because of chance, because of the stochastic behavior of the system, we had to do something multiple times. We had to try it multiple times because different outcomes could happen even though we took the same action from the same state, right? And then it's hard. When is the right time to stop pulling that red lever? Because you could have just been unlucky the whole time, right? That slot machine could give you $2 with 0.99999 probability. And we just happened to end up, whatever, 6 sigmas to one side in the luck meter, right? And so, when do you decide? When do you decide I know enough? Maybe you can interleave these things, I don't know, right? It depends on your goals. But this is a lot harder than just saying, I know the system, I'm going to solve it. Yes?
So is this like where generation learning comes into play, where you have a whole bunch of agents doing the exact same problem, and then you pick the generation that did the best?
So I think you're describing kind of evolutionary computation, or genetic algorithms, right, or kind of a piece of evolutionary computation. That is a type of machine learning algorithm that can be applied to a bunch of different types of problems, including there are some hybrid approaches between reinforcement learning and GAs, genetic algorithms. We will touch on genetic algorithms later in the semester a little bit, but the way they relate to reinforcement learning is kind of a very cutting edge of both topic, and so we're not going to cover that at least today. But yes, that is a machine learning algorithm. The idea of having multiple things running at the same time and then kind of choosing from that set, and then maybe sharing information between those things based on what each of them learned under different initializations. That's all very, very good ways to start thinking about solving these problems in practice. That makes sense? Okay. Questions about MVPs? Questions about slot machines? I don't actually know much about slot machines. Questions about these slot machines? Okay. All right, let's move on to reinforcement learning for realsies. And while I switch the slide set, let's take 5 minutes.
Okay. We do, because this is 100, but then this is out of 15. So yeah, people are like kind of predicting. This is out of 5. Project 0 is out of 5. I mean, 5 kind of confused.
Why does that look like that?
Maybe the button on the top right. When you go to present,
I'm just going to do this. Just start over.
okay. Because
If this doesn't work, then I'm going to share knowledge, iPad, PowerPoint.
so for project 1, the grades are out of
Where's should this be?
certain number.
Instead of like 15.
Okay, so there's a mismatch between the canvas points. I've described it in, okay, let's make it out of, we haven't put any grades in, right? So let's make it out of 10 and just do 21.
Okay.
This is out of 100 total, right?
Yeah.
And that's including everything.
Yeah.
So let's just change the point total. Actually, I wanted it to be 15.
So what's the relevance of 15?
Well,
Because you're saying it's 3 times as
it's
much.
3 times as much as we'll just make it 10.
Or could we do the opposite and just scale project 1
That just
to 33?
I mean, we can do that, right? We can take whatever percentage of 100 and multiply that percentage by 13. Depending on canvas. But that sounds like it's probably calculator error. But actually, that's what I'm going to do.
Okay, so just convert from 100 to 15.
Yes.
Okay. So maybe we just like make like that after we do these.
Yeah. Yeah, so for project 2, let's make a PDF out of 150. And we'll make the point 15. Does that sound good?
Okay.
And so we're moving pretty slowly. So I'd like to get home and
Okay.
so once you feel confident, it would be better if you guys verify in detail. But at this point, like we're just running. So I want to share drive or right. I can look at it, but I will. You guys okay. Cool. Alright, so let's try to get that.
Next, please.
Oh, let me think about it. There should definitely be an MVP in this stuff. So you can start working on the show. The final grades will be.
I mean, how we decide based on that final.
So for now, I plan to but we'll see.
So you will possibly
That's not good? Yeah. Okay, let's get started. Is everybody back? Raise your hand if you're not back. Bad jokes. Bad jokes. What I got. Okay, let's get started. All right, so we're moving now into reinforcement learning, which is one of my favorite topics in the whole set of AI curriculum that we're going to cover this semester. Reinforcement learning is one of the hottest current topics in AI. It's one of the hottest current topics in machine learning. It's one of the hottest current topics in robotics. I have strong feelings about how that works, but I'm not going to get into them now. You can talk to me about it another time if you'd like. But very, very exciting results are happening right now on the cutting edge of all three of those very related fields. I'm in favor of it, by the way, my strong opinions, but with some caveats. Anyway, not important. Okay, very, very exciting things are happening in AI, machine learning, and robotics, among other things. But those are kind of my 3 areas myself. So I see these results a lot. Based on reinforcement learning. So, if you're not excited about reinforcement learning, I don't know. What are you excited about? We'll probably cover it. But to each their own. However, I find this to be one of the most exciting topics in the course. Okay, reinforcement learning. So the idea is, kind of in a broad, very, very broad, very overly simplified sense, we have some agent. That agent does things, and it accumulates rewards as a result. So we have this little guy trying to get the gem for obvious gem-related reasons, and it needs to learn how to do it. Right? Okay. So the idea here is basically we have some agent. This agent takes some actions, right? Those actions then influence the environment, or the state is influenced by the environment as a function of those actions, whatever. And then as a result, the agent gets some reward. There's some state transition that happens based on the relationship between the agent, the action the agent took, the environment, right? And it all happens again, right? This is reinforcement learning in a nutshell. So I receive this feedback in the form of rewards. This is very similar to what we've been talking about so far. The agent's utility is defined by this reward function. It must act so as to maximize its expected rewards, but it has to learn to do so. Right? All the learning it's able to do is based on observed samples of outcomes. That's overly restrictive maybe, but it's a good way to think about it, at least for now. Okay. All right. Let's look at some examples real quick. So here we have a snake robot. So it's just some segmented robot. It's got some motors. It's able to move the segments' orientations with respect to each other. Right? And there's a bunch of these linked together. It's a snake. The idea is that they want this snake to be able to get up onto this step and then to move in a sidewindy way over the step. So the snake has to learn how to get onto the step. And so they did reinforcement learning, and the resulting policy looks something like this. It's pretty impressive. If you had to describe to this robot in advance, so that's its sidewinding motion. If you had to describe to this robot in advance the right way to actuate its motors in order to get up on that step, how hard would that be? It would be very difficult. Right? So reinforcement learning was the strategy used here that learned a policy that allowed that robot to be able to perform that. All right, here's something that hits very close to home for me. This is a toddler robot. So I have a toddler that does all kinds of toddling at home, and so I used to watch reinforcement learning from a biological sense in action. He hits his head on stuff way more than I would think would be the right answer, but I guess that's the exploration versus exploitation issue. But anyway, back to robots. So this is a toddler robot. The idea here is that they made this robot that kind of had curved feet that was able to kind of rock back and forth, which is what toddlers do a lot. Anyway, and so they wanted to make this thing walk. So this is kind of the general motion of how it would work. And they designed it such that if there's a slope, if it's on an incline of some specific, in some range of inclines, some specific range of degrees, then it just kind of passively walks down the slope. But they want this thing to be able to actually kind of locomote when there's not some specifically described slope in place, right? And so after some set of iterations in a reinforcement learning setting, they produced a policy that resulted in actions that look like this. Right? So that thing's really trucked along. Right? Let's look at this crawling robot. So this is a simulation of a very simplified system in which we have this robot. This robot has two joints. It has a rotational joint here and a rotational joint here. right? There's some physics simulation, which basically says you can't pass through this, that's the ground, it relates these things together. The idea is that this thing wants to learn to move. And so what you have is the ability to move those joints, to rotate those arms, the first with respect to the box and the second with respect to the first joint, right? And so from a reinforcement learning sense, what you would want to do is figure out, if I have a setting, a specific set of two angles that these arms are at right now, in what way do I move those, that's the action space, in order to locomote, right? Okay, so if we look at what that might look like, here we have it early in the learning process, kind of exploring the world, and by the world I mean the set of state and action pairs and the resulting rewards. So this is the robot kind of figuring out, it's a simulation of a simple robot, right? Figuring out how it would move its joints in order to move around, and it's trying a lot of things, and it's having various degrees of success, and it's doing a lot of things that don't work very well, right? At some point, if we skip ahead a bunch of iterations and take the learning rate down, this epsilon value is the kind of exploration. But if we remove that and skip a bunch of steps, this is the policy that it's like. Cool, right? Okay. That was a little while ago, so let's look at something a little more modern, but it's very related. Oh, it's Prince. So let's look at 5 seconds of this Prince ad. So this is a more complicated version of that crawling robot, right? We have this kind of physics simulation. We have this 3D set of limbs that are capable of moving with respect to one another. And through a type of reinforcement learning, the engineers at Google were able to have these learn how to kind of locomote in their environments in a bunch of very specific and interesting ways. So nobody told these agents what walking looks like. That's how I run. I don't know about you. That's my victory pump. That's exactly right. Right, so all of this was learned behavior based on reinforcement learning. So. So that's this notion of exploration versus exploitation, right? You have to try things that don't work in order to learn. And the really interesting part is coming up here. Again, that's what I look like when I'm running. So this strategy here, right? That's not really something that looks like where you kind of hand coding the behavior that robot would have it do, right? But it was able to learn some policy that was just like show, tune, shuffle, right? That allowed it to jump over gaps more effectively than the other strategies that had explored at the time, right? And so people are using these to kind of come up with behavior that looks unexpected but outperforms hand-tuned or hand-described versions of these agents. It also gets to this notion of local minima in the optimization. You could have a local minima that behaves reasonably well, but there's some other global way that your reinforcement learning, whatever your optimization and your reinforcement learning algorithm is doing, hasn't discovered. Right? The specifics behind that will become much more clear over the coming weeks. But that's kind of an introduction to maybe what kind of modern reinforcement learning things, without getting into a lot of examples, are doing. Okay, reinforcement learning. So The reason we covered MDPs beforehand is because MDPs are very interesting in their own right. And you should, if you can frame your problem as an MDP, you should do that because you can solve it offline. But let's say you don't have some of the same information. So in MDPs, we had the set of states, we had the set of actions, we had our conditional probabilities describing these transition functions, we had reward functions that happened when you landed in a state, right? And we were looking for a policy pi. We're still looking for a policy pi that maps states to actions. That's going to be our outcome of reinforcement learning. But here's a new twist. We don't know T and we don't know R necessarily in advance. So this means we don't know what states are good, what actions are good, what happens when we take our actions, what good actions are, none of this, right? And so that means we actually have to try things out in order to learn. So if we take our overheated car MDP that we've been running with, the corresponding reinforcement learning setup would look like this. Less information, right? So the takeaway here is that we do not have. Okay. So I kind of touched on this distinction between offline and online, right? MDPs are offline. We have some specification of the behavior of the world. It is sufficiently detailed that we can reason about it in advance, right? And so we can say, if I were to take this action from here, that would potentially land me here with some probability, and if I were to take this action from there, that might land me in this state with some probability, on and on and on. That reasoning process is what we described when we talked about ways to solve MDPs, right? But this reasoning happens in advance, it happens offline. Online learning is different. You have to try things, right? So in this example here, this robot has to jump off the cliff in order to learn that that's not fun. It has to do so in order to learn that there's fire down there, essentially. It has to try things, right? And so we're going to be talking now about online learning. Reinforcement learning is an instance of online learning. Okay. In online learning, we're going to break it into two categories, model-based learning and model-free learning. Okay, so let's talk about model-based first. So the idea here is that we're going to learn an approximate model, an MDP model, based on our experiences. And then we're going to solve that model just like we were solving MDPs, as if it was the true model. Okay, so step one, learn your MDP. That means we're going to count how many times S prime happened for each S of A and use that to approximate our transition probabilities. Right? We can normalize that and we get this approximate transition function. Right? And then we're going to discover these rewards as we do it. Right? So we explore the space, we do some things, we keep track of what happened. We use this to build up an estimation of an explicit MDP. We are keeping track of the transition probabilities. We are keeping track of the reward functions. We are building the model. That's the model in this model-based learning, in this instance of model-based learning. There's other kinds of model-based learning. That's what I'm talking about. Okay, so once we build up by looking or exploring this approximate MDP, we just solve it. We solve it like we've been solving MDPs for the last 2 weeks. Right? Use value iteration or policy issues. Okay, so here's an example. Here's our world, right? But the agent doesn't know anything about this world. So this is kind of hard to show, but we can look at this and kind of intuit some structure to this world, right? We can say, based on how we've seen grid things work in this class so far, it seems like we're not going to be able to go from, say, A to D, or A to anywhere else, or E to D, without going through C, right? We can kind of intuit that, but that's not how it works. Beforehand, we don't know any of this, right? We have to figure this out on the fly. Okay, so let's say we've observed some set of runs. We have watched an agent move through the space, and we got to observe what happened, right? So we see a state, we see an agent chosen, we see the resulting outcome, and we see the reward that was associated with that outcome. And we see a set of those rungs, right? Then we can start to build up this set of this model that we're learning, right? So we can say, let's say that we're looking for the transition probability, or the transition function, if we started in B, chose east, and landed in C, right? We can say, well, I saw that happen. I saw this choice, this action state pair happen, right? And the outcome was this 100% of the time, right? So we can say, under our observations, this probability is certain. We can do more, right? We can say, what's the transition probability of starting in C, choosing east, and landing in D? Right? So let's see. When did we have C and chose east? We had it here, we had it here, we had it here, we had it here. Right? Well, this is a little more interesting. We just count them up, right? We saw this happen 4 times. We saw this happen 4 times. And we saw this outcome happen 3 times, right? So this then is going to be 0.75 according to what we've seen, right? And we know also that C east A, based on the same set of observations, 0.25, right? And we can do this for every pair, every state action pair, to come up with an approximation based on the counts that we've seen happen in practice of the transitions. We do the same thing for rewards. So that may look something like this, right? Well, now we're done, right? We solved it. Is that true?
We can't really be certain.
In what way?
Like, we don't know if we know the exact probability.
Right. Yeah, maybe in some instance, what we observed was unlikely to happen and is not a good representation of the true variances. Yeah, that's a great point. More specifically, we've reached this step, we've constructed the model. We now have an unsolved MVP, right? So we're not done. We have to solve the MVP. We just constructed an approximation of the MVP, right? Now we have to go back to the slides from last lecture and the video or the lecture before and figure out how we solve this, right? So we've constructed the model. We have to solve the model using whatever strategy you would like, right? So this is kind of where we're going to stop with model-based learning for now. Most of what we're going to talk about for the next lecture and a half is going to be model-free learning. But are there any questions about model-based stuff before we move on next time? Questions? Yes?
When do you stop building the model?
When do you stop building the model? When you run out of time and you have to start doing stuff. Maybe. Or maybe after some fixed number of iterations. Or maybe you look at a probabilistic approach to when you decide the odds are you've seen enough, right? Which we'll talk about later in the session. Okay, see you all on Thursday.